velocity doesn't have meaning if there's not a frequency that's available. In other words, if it's a wideband, like a transient waveform or something like that, you don't really have a phase per se. You all follow me? So when you talk about phase velocity in general, we're talking about propagating phenomena. And let's go with the general form of propagating phenomena. You're going to have some E field. There's going to be some magnitude, E naught. And there could be a loss, so it could be E to the minus alpha z. I'm going to have it propagating in the z direction for simplicity. And that's going to be times the cosine of, technically it's omega t, and I'll have it propagating to the right, so I'll be real clear. It's minus beta z. And there could be a phase angle. Typically, that's phase angle, it's not going to have any bearing on us. I'll put it in the AX direction, make it volts per meter. Here's a standard. Yeah.
I have an additional question. So if it's E naught e to the a minus alpha z, how is that going to affect our going to the phase domain?
Phase what? I'm getting there.
Okay.
You're way ahead of me. You all with me? I'm just showing you a general equation. Now it's lossy, because I'm going to go ahead today. The last thing I'm going to do is phase velocity and all this business, electric fields and all this thing in lossy media and in conducting media. All right? So anyway, here we go. So in general, if you have this type of thing, there's a propagation constant. The propagation constant is square root of j omega mu times sigma plus j omega epsilon. Now that's assuming that it's at a constant frequency. This doesn't have a meaning if it's not. Y'all with me, class?
Yes.
All right. So this is equal to alpha plus j beta, right?
Yes.
Now, if you look at this, what if sigma is much, much greater than omega epsilon? Then all of a sudden this, sigma mu times omega would dominate, and then with this term we could ignore, right? That's a good conductor. And then we'd find out that this has a real and imaginary part that are both the same magnitude. I'll show you this in a second. You'll see this. So in general, the phase velocity is the rate that this thing is moving, the phase of that moving. Think about that. If that's constant, right, that means the cosine of that is a constant, or that we could just surf on top of that point at a certain velocity. So here, I'll put some, I'll just call this is equal to omega t minus whatever this is, beta z plus phi. Now, I want to make sure that I track how fast that thing, that angle is moving. So I take a derivative of this, and I get 0 is equal to omega, a derivative of this with respect to t, minus beta dz dt. Phase angle doesn't matter over there, this one. Right? I set it equal to 0, and I find that dz dt.
Why do we set it equal to 0?
Well, when you take a derivative of something with respect to time, right? If that's a constant, right, it's just the argument, it's 0, isn't it?
Ah.
Right? So what happens? That and that survive, and you get dz dt is equal to omega over beta. This tells you the direction of the wave is going to be the positive z direction. And this is called phase velocity, right? This is equal to the phase velocity. Do you all agree with this, class? Just,
Yes.
I've said this. Now, so that's how you get it. And technically you get omega and beta. The bottom line is from this equation. It'll always work. So let's take a look at beta and omega for lossless and then lossy materials. We're actually going to do good conductors in a second. So since you asked this, it's a great question. It's a lead into exactly what I was going to talk about. When I look at this, and I didn't plant that question, so suppose that sigma is 0. The minute you see sigma is 0 or alpha 0, it is lossless, right? Do you all agree with me then?
Yes.
That's loss. That's the definition. Either sigma or alpha equals 0. This is lossless. There's no power dissipated. The wave is going to have the same magnitude if it's a plane wave propagation. So if that's the case, then gamma is equal to square root of j omega mu times simply j omega epsilon. You're asking about this, so I hope I'm answering your question directly, right? There's no sigma, correct?
Yes.
Just look at it. All right, so I got j omega squared. Square root of this is just j omega. Then I have times the square root of mu epsilon. right? Now technically that's equal to alpha plus J beta, right? Well, you can see it's 0 is the real part over here, right? I could put 0 plus this, but it's kind of a waste of time, isn't it, class? So alpha, by inspection, is 0. You all follow me?
Yes.
Now you take a look at this. What is beta? Well, beta is a coefficient in J is omega times square root of mu epsilon, right? There's no tricks here. I'm just stating the obvious. Do you all agree with that? Now, if that's the case, what else? What is phase velocity? By definition?
It's omega over beta.
And what is it?
That's going to be 1 over the square root of that.
Mu epsilon. Generally speaking, if you know mu relative and you know epsilon relative, you know the phase velocity, because this is really phase velocity is equal to c over square root of mu relative, epsilon relative in this case. C is about 3 times 10 to the 8th meters per second. It's not exactly, but it's close. 2.99 something or other. And then if you divide this by square root of mu relative, epsilon relative, lo and behold, you have the phase velocity. You all agree with that? Now something else to be said. Most, if not all, of the stuff that we worry about propagating wave phenomena being in is non-magnetic. Most of it, at least in my world. You get magnetic materials if waves are propagating in things with iron filings or space. When you talk, actually, but then it's not. If you're talking about a plasma, like the ionosphere, propagation occurs in both sigma, epsilon are tensors, and to be frank about it, they're not truly magnetic tensors, but because the magnetic field of the Earth, this is kind of a crazy, it will cause a pseudo kind of mu relative non-zero, not one effect, but don't worry about that. That's way beyond the scope of this class. Just realize that most of the time, when we talk about propagating phenomena in our little world, it's not going to have a magnetic, it's not going to have mu relative be anything but 1. You all with me? Water, that's a very lossy material, but okay. So that's it. Now did you have a follow-up on your thoughts?
Oh, that's what I wanted specifically. You got me what I wanted.
Now I'm going to give you what you didn't ask for, but is a logical extension. It's
Yeah.
what happens if you're in a conductor, all right?
Yes.
Matter of fact, let's make it a good conductor. Now I want to tell you this. If you're given a field, and I'm going to do this. That equation will work, but I want to do this. Let's start from here. Now, if you're given any material at all, and you don't know if it's a good conductor, a good dielectric, anything like that, but you've got a wave that's being excited by an antenna, say, that's got a cosinusoidal variation at a given frequency. You with me? That's causing the phenomenon. And the first thing you always get is gamma. Gamma is square root of J omega mu sigma plus J omega epsilon. Now, we already found out, I mean, this will do it. If you have a value of sigma and you have some epsilon and sigma's not 0, you punch it into this, you'll get both alpha and beta. No questions asked. You all with me? And by the way, for this one, if you get alpha plus J beta here, and you want the phase velocity, it is simply omega over beta. End of story. It'll always work. However, if you're talking about a good conductor, slow me down if I need to slow. If we're talking about a good conductor, and I'll do it here. Well, what is a good conductor? It depends on the frequency, but it's when sigma is much, much greater than omega epsilon. That's the condition. You can see it as frequency dependent, because what if you're a DC? Well, if you're a DC, anything's a good conductor. There's no omega epsilon. You all follow me on this class? But generally speaking, when you're talking about anything, it depends on the frequency, and I might add something else too. The value of epsilon can be frequency dependent. As a matter of fact, it is. There are regions where, for instance, water is distilled water, light goes through very easily. You change the frequency and lower it down the microwave range, and all of a sudden, it doesn't penetrate at all. So, and the reason is epsilon relative is a function of that and epsilon double prime, which is a loss that you don't know about. Actually, you might. No, you don't know about it yet. But the characteristics of matter are very frequency sensitive. It's very important for you to appreciate that. What happens in the microwave, that's 10 to the 9th hertz, 10 to the 10th hertz, even 10 to the 11th hertz, is not the same as 10 to the 15th, 10 to the 16th, like optical frequencies. Much, much different properties. So you got to be careful about this. But if this is the case, you got a good conductor. What's a good conductor to you in your own ideas? There's a lot of examples. Think of a material. Copper, silver, gold, aluminum, steel. Anything that it has low resistance to electricity that you already have been exposed to. What's a bad conductor? Mica, diamond, air. Right? Air is not a very good conductor. Stuff like that. You all with me, class? So, and that's general, by the way, but it is frequency dependent. Right? So, now suppose this is the case. You got a good conductor. And by the way, this is an interesting part. So now look at gamma. Gamma is equal to the square root. Normally it's j omega mu times sigma plus j omega epsilon. Now we're assuming this. So this part goes away. We can ignore it. You all with me, class? And if we can ignore it, what happens? You get j omega mu sigma. Now go with me on this one. This marker has seen better days. Long for the day that they use good markers. Now we talk about the square root of j for a second. How do you render j? What's another way to say j?
The square root of negative 1.
It's equal to the square root of minus 1, right? That's one way of rendering it. It's also equal to what? E to the j pi over 2, isn't it? That's 1 at an angle of 90 degrees. Isn't that
Yes.
So, I mean, you can call it 1 at 90 degrees. 1 at an angle of 90 degrees. That's the same thing. Do you all agree with this?
Yeah.
Make sure you see this. All right. So what's the square root of j?
The fourth root of negative 1.
And? You're right.
Square root of e to the j pi over 2.
That's the same thing as what? E to the j pi over 4, isn't it? Right?
Yeah.
Shocking. Come over here for a second. Now, I better keep going on this stuff. So what is e to the j pi over 4? Think about back in the day when we did Euler's, which you guys, it should be second nature to. What's Euler's equation?
E to the j theta is cosine theta plus sine, or j sine theta.
All right. What's the cosine of pi over 4? Cosine of 45 degrees? 1 over square root of 2. Right?
Yeah.
What? Yeah, same thing. What is the sine of 45 degrees?
Same thing. Same thing.
1 over square root of 2. 1 over square root of 2 is shocking. So this is cosine 1 over square root of 2, or 1 over square root of 2, plus j 1 over square root of 2, or it's simply j plus 1 divided by square root of 2, isn't it?
Yes.
Y'all with me? Okay, come over here. I got a square root of j there. Another shocking fact. Square root of j can be replaced by 1 plus j over the square root of 2, right? That's right here. Times the square root of omega mu sigma. Y'all follow me on this?
Yes.
Almost there. Just bear with me. This is for a good conductor, correct? Now, watch. That square root of 2 I can bring under here. I can actually make this root 2 right here, can't I? There's no tricks here. I'm just shoving things around to make it a little easier to see. Agreed, class?
Yes.
All right, if that's the case, what happens here? I have 1 plus j. Well, what is omega in terms of f?
2 pi.
2 pi f. So it's times the square root of pi f mu sigma. Okay? Now this is interesting. I've got to erase this to show you. All right. What does that mean? It means my propagation constant, which is alpha plus j beta, if it is a good conductor, alpha is equal to beta, and it's also equal to square root of pi f mu sigma times 1 plus j. Y'all follow me?
You said it's a good conductor, alpha equals beta?
Look. Alpha is the real part.
Oh.
Beta is the imaginary.
I got you,
That's
got you.
interesting.
Yeah, it is. We're not done yet, though.
Oh,
Y'all
we're
with me?
not.
This is a very good thing. But by the way, this is it should be interesting. It'll save you so much on everything. All right, now I've got that, right? So I have alpha equal beta equal the square root of pi f mu sigma. That's one way of writing it. I can also write it as what? Square root of omega mu sigma over 2, correct? That's another way of writing it. Now watch. Y'all with me? All right, so let's talk about some stuff with a good conductor. First, what is phase velocity with a good conductor? This is all good conductor.
It'd still be omega over beta.
It has to be, right? Let's keep looking at this for a second. Y'all with me, class? I'm going to manipulate this. So it's omega divided by beta. I'll use that form of beta so you can see it. That's omega mu sigma over 2. And y'all see what I'm up to, right? So, all of a sudden things are getting interesting. How can you manipulate this? Well, this is really omega mu sigma over 2 to the 1/2 power, right? What does this become? Isn't that equal to the square root of omega, right? Divided by mu sigma times 2. Take a look, see if you believe me.
Wait.
Y'all with me? Take a look, make sure you believe me.
Makes sense to me.
Wouldn't the 2 be in the, oh wait, the 2 is in the top, never mind. Yeah,
You agree with
that's
me?
good. Yep.
Why don't you take a good look at that? What's the phase velocity if omega is 0?
0.
Wow, that's kind of slow. What's the phase? I mean, you can see the phase velocity can be much less than the speed of light. The old professor who used to be here, Tom Shumpert, used to say, well, I can run faster than the speed of light in materials that are very good conductors. That's sort of true. Depends on the frequency more than anything, if you look at that. So this is the phase velocity. Now, so what does that mean? Because if people say, well, that means, you know, what actually happens? Now, here's the deal. This is physics. I mean, this is actually probably fairly advanced physics. But when you talk about that being the speed, that's the bulk speed of light, the apparent speed of light. Photons always ricochet and move at the speed of light, always. What happens when you get a good conductor? Now these things are banging around, and most of the velocity is doing this to the photons. They're hitting things, they're going like this. I hope you can appreciate what I'm trying to tell you. In other words, if you looked at the actual total path that a photon went for a given second, it would be 3 times 10 to the 8 meters per second. But the horizontal displacement, the net effect is the actual waves moving this way, will still be that velocity. That's the phase velocity. You with me on this, class? It's a little deep to think about it. You can have, it's the overall effect of all the ensemble of photons are moving with that phase velocity in a given material, a given conductivity. The actual, a single photon, if you could somehow jump on it and watch it, would always move at the speed of light. This is really one of these things where it's banging around and it's losing energy too. A lot of energy is lost. And this is kind of getting into more of the fundamental physics. It's advanced physics. And it's getting to an area of physics called quantum electrodynamics, even though this isn't true quantum, that gets a little tough to understand unless you're right there taking all the coursework first. Okay, anyway, that's the phase velocity. So, if you have, please listen to me now. Suppose I got a big fat copper wire, like so, and I have current flowing this way in the wire, right? And it can be in a coax cable, but anyway, I want to focus on this. What you're going to see is this. As current, if this has a given radius A, and I just want you to appreciate the big fat wire. Right? When the electric field will be on the surface, it'll short out before it can get any depth into there, because the wave, when you actually have this, there's a wave that's propagating from the surface of that copper wire towards the middle. The electric field is in this direction. Think of this, the electric field is shoving the current down this way. Really, it's a voltage, but it's going to develop an electric field on the surface. The actual magnitude of the electric field as you go into there will short out like crazy. Alpha is going to be the same as beta. It won't go deep, but the rate that it's flowing towards the center of that wire, you could say the wave velocity there, is going to be that phase velocity. It can be much, much less than the speed of light. The actual propagation of a good conductor, like this, you know how we have coax cables and stuff like this, right? When we have wave propagation on a good conductor, there's going to be an inner and outer core. Just let me back up for a second like this. The actual electromagnetic propagation that occurs, there will be a very small component of the electric field in that direction. I might say shove it, but there will be an electric field. The major electric field component is this way or that way, and it's propagating in that direction. You all follow me, class? This is like something that's containing the field, so it propagates that way. And that's really it. You all with me? I hope he's coming back.
He has his bags. Probably uses the restroom.
All right, so that's the phase velocity. All right, part two. We're not done yet. What's the intrinsic impedance? I know, you're probably just dying to know. But it's important that you do a good conductor, because this, I'm telling you, there's a lot of stuff here that makes a lot of what we do in engineering, electrical and computer engineering possible. So, what is the characteristic impedance of the media in general at a given frequency?
The square root of
120.
J omega mu over sigma plus J omega epsilon.
Yes, that's it, right? Now we made the assumption it's a very good conductor, didn't we?
Yes.
So what do we do?
The sigma is much, much greater than this, so J omega epsilon is irrelevant.
All right, everybody watch this. Make sure you don't miss this, because it'll be on the font. So this goes,
Can you repeat that?
this goes on the font.
No. What? Past.
Plus J omega mu, right? I mean epsilon, pardon, right? Isn't that the conductivity? That's the intrinsic impedance of any material at a given frequency. Do you agree with this? It's an excellent guy. I'll go with it. All right? Yeah. Right?
Yeah.
Now, if it's a good conductor, because that's what we're talking about, good conductor means sigma is much, much bigger than this guy, right? That's the definition.
Because it's negative.
Yeah. You're just saying sigma dominates the magnitude of J omega. What is this? Well, a couple ways to look at it. Isn't it really equal to the square root of omega mu over sigma e to the j pi over 4, or square root of omega mu over sigma e to the j 45 degrees ohms? Take a look at that. You all agree with that? Now, anytime you have a an intrinsic impedance, that has an imaginary value, you know it's lossy. So, look at this. This is for a very good conductor. And a very good conductor, the phase angle is 45 degrees. It's a big loss. I'm just telling you, that's a lot of loss. We saw that alpha and beta for a good conductor would have the same magnitude. It'd be the square root of pi f mu sigma. You all with me? This is just something, if that's the conductivity, and now, hear me now, let's say I've got the E field in the phasor form. You all know you're going to be asked how to turn an E field and H field into phasors, even on the quiz today, right? Even on the quiz today. All right. I try. I really try. All right, ready? Okay. Now, if that's an E field, what's the phasor form of that? E naught, right?
Yeah.
Phasor form, still E to the minus alpha Z, that's, and then what? It's going to be E to the minus J beta Z, right?
I have a question. Why does the omega t not?
Do you know the definition of a phasor?
Okay,
The way we did it?
I'm fine then.
In circuits, do you remember how they do it?
Not particularly.
They assume that the electromagnetic event is going to have, voltage or current is going to be E to the J omega t, right? Plus a phase angle. So they write the differential equations, and lo and behold, on both sides, E to the J omega t appears.
So they cancel.
They cancel it. Then they say, we know omega, so now we're talking about phasor voltages, magnitude, angle, magnitude, angle.
What about your phasing?
If there's a phase angle, then it goes right here. Think about that. That's a plus, right? So it'd be E to the plus J phi 1. With me? But that's an implicit phase angle there. And usually it's zero. I'm going to make it zero just to let you appreciate what I'm trying to tell you. So if this is the case and it's AX, this would be the phasor form of E, right? Y'all with me?
Yes.
If that's the phasor form of E, it's a propagating wave, isn't it? What?
I was just thinking that like alpha and beta are equal, right?
If it's a good conductor, absolutely.
Okay.
Yeah, they will be. But I'm going to leave it like that because we usually break out alpha and beta. So if we go to the time domain, we can easily take the alpha out front, leave the beta alone, put it in the omega t. Put it in the argument of cosine. Y'all with me?
Yes.
So assume that from now the eta has some value, call it eta naught, and it's at an angle E to the J pi over 2. Pi over 4, pardon. So it's a good conductor. So if that's E, what's H? Remember I told you the trick? It's what? H is 1 over eta, right?
AP cross with E.
Unit vector in the direction of propagation crossed into E. Y'all hear me on this?
Yes.
That's the phasor form of E. We're not done yet, but you're going to be shortly. Everybody with me? Okay. Now, what is this? Well, that's 1 over eta. Eta now is going to have eta naught, right? It's E to the J pi over 4. This is for a good conductor. I'll make it E to the J 45 degrees so you guys, this is not exactly kosher, but I'm going to do it because you've got a better handle on 45 degrees. Then it's direction of propagation. What's our direction of propagation? Assume this is a good conductor. Take a look. Come on, guys. Look at the waveform. What's the direction of propagation?
Oh, it's in the plus Z direction.
Does everybody hear me? Hear him?
Yes.
Plus C, right? How do you know? You look at the coefficient of
Beta.
beta Z. You want to see if it's plus or minus something. If it's minus, it's going to the plus Z direction. So that means it's AZ crossed into the E field. And my E field was what? E naught? E to the minus alpha Z, E to the what? Minus J beta Z. I know they're the same, right? I've got rid of the phase angle intentionally, AX. Now, what does that mean H is? Take a look. I'm right here. I'm going to get out of your way. Just take a look. I left beta naught as just a constant. It's the square root of omega mu over sigma. And it's not really. Maybe I should do this. Call it eta prime. And call eta prime here equals square root of mu sigma. Square root of omega mu over sigma. So, there we go. Make that eta You all with me on this? I'm doing this to just distinguish it from the value of free space, A and I. With me, class?
Yes.
Come over here. What is H? All right, let's do it. First, what's AZ crossed AX?
AY.
You all agree with that? So it's in the AY direction. I'll put that out in front. Usually it's in the back. Now, what happens here? I have E naught over eta. That's going to be a value, a single constant, right? So I have E naught over eta prime. That's a magnitude. Now I have all this, right? I have e to the minus alpha z, e to the minus j beta z. Please watch this. You all with me?
Mm-hmm.
But I have to account for this e to the j 45 degrees. And now I say this. What is 1 over e to the j any angle?
It'd be e to the minus j.
That's right, isn't it? Take whatever the sign is and flip it. You all agree with that? All right, bless you. What happens then? This becomes e to the minus j 45. You agree with that? And you can add it to the beta term. So now I have this times e to the minus alpha z, e to the minus j. Now remember, that was positive becomes negative, so you can just take that and put it as beta z, and you can put plus 45 degrees. And now you have the H field. Y'all with me? But you'll notice that the H field and the E field are out of phase by 45 degrees. And that's as much as they can be out of phase with each other, no matter how good the conductor is. Typically, they're in phase. As the E field increases, the H field increases. But the greater the actual conductivity is, the more out of phase they are. You with me, class? All right. Any questions about that?
Nope.
I figured. I mean, this is something that's interesting. I'll give you a few problems on this, and I'll come the final exam. You will get a problem related to that. Not a difficult one, but a problem. Okay. One last thing, and this is the last concept we talk about in the class, that I talk about at least, is going to be the concept of power. And we talked about the pointing vector, just to get the idea of the direction. But here, this is the only thing you're going to do. By the way, I've enjoyed this class. I know it's small. I haven't always been the sharpest knife in the drawer when I'm up here because I was tired. Being sleep deprived is one of the things I hate. I have a dog. Animals and thunderstorms don't get along. So, now, this is power. And really, it's pointing vector. The form of the pointing vector that you'll see in most textbooks, not in ours, is S. And what that is, it'll be instantaneous. It's a function t in spatial form. Is equal to simply E, that's a vector crossed into H. This is for propagating, this is for power flow. So E and H you cross and we get it, but this is instantaneous. Almost always we talk about the average value of this, and this is in the book, it's called P-Av. It's a function of Z only. And it's 1/2 the real part of E crossed into H conjugate. That'll always be that for propagating waves. It's very similar to, if you think about when you had circuits, you learned power was what, 1/2 V times I conjugate. Remember that? And that would be average power. This is average power. The units of this are watts per meter squared. Now, I'm going to tell you one thing about this. This is important you see this. Remember how I showed you this? And there's that 45-degree angle that I can account for over here. So if you have power flow, and I'm only going to go in one direction. If you have power flow, so I'm going to assume that the direction of propagation, or V phase, is plus Z. Then the average power flow in the direction z is 1/2 the real part of E. Well, E is equal to E naught, right? And it's going to be e to the minus alpha z, e to the minus j beta z in the AX direction. And it's crossed the H field. We just did the H field there. The H field is equal to E naught, right, over A prime e to the minus alpha z, right? But hear me, it's conjugated, right? So I have to put, look right here. See this H?
Yes.
Yes. With me, Hayden? When I conjugate it, that means I flip the sign on this J term. So now this becomes e to the plus j beta z plus, I'll call it pi over 4. Just work with me on this one. And that was AX, that should be AY, right? Can you all follow me? Just take a good look at this. It's in the book, but I want to do this for completeness. Everybody with me?
Yep.
You good with that? You should buy a mechanical pencil. Oh, yeah, I do that too. But I don't even use mechanical pencils. I just use, honestly, I use felt tip pens and I'll just cross out stuff I don't like. I'm tired. All right, now look at this for a second. Here comes the average power. All right, first I got a 1/2. That's going to stay. You'll notice I have E naught twice, right? So I'm going to have 1/2. I'm going to have E naught squared. Now I have eta prime. That's a real value, right? So I just put magnitude of eta prime here. It's got to be a magnitude. Keep watching. Now I have e to the minus alpha z and e to the minus alpha z twice. It becomes e to the minus 2 alpha z because it appears twice. You all with me? Then you come down here and notice this. Now I have e to the minus j beta z here, but I have e to the plus j beta z there. It cancels the phase term entirely. You see that? Mm-hmm. E to the a times e to the minus a is e to the 0 is 1. Agreed, class?
Yes.
You with me, Zach?
Yeah, I think so. Why is it negative right there in that H?
What is negative?
The negative J. Is that minus J?
Yeah.
Oh, it's because the
Probably
original
should-
cosine was minus beta z, so it's minus.
Oh.
That's what we're, yeah, I erased it. Yeah,
Oh,
it's
gotcha.
propagating the plus z direction.
And then it was 1 over j to the 45, so that's why it's minus 45.
That's right.
Gotcha, so flip.
Okay, you ready? Now, I might as well go ahead. So the betas cancel. That there's still going to be an e to the j 45 degrees. You see that?
Mm-hmm.
The real part of 45 degrees is actually I'll just put the cosine of the phase angle of eta goes here. So of eta prime. So this cosine, that'd be the cosine of that. That's the real part. You all with me? It's somewhere between cosine of 0, which is 1, and cosine of 45 degrees, which is 1 over square root of 2. I'm going to leave this cosine of that. And then it's going to be ax crossed ay is az. Now, you know the direction of propagation. The pointing vector has to be in the direction of pointing. You're pointing in the direction of propagation. But that's the power density in watts per meter squared. It's a very important concept because that power density, believe it or not, tells you a lot about how much power you can put on target and then get reflected power from it. There's a lot of things that are very important about this. This is the last topic before your quiz. And before this, we'll close this up. I'll give you some problems related to this week. And then on Monday, I'm going to go through and do the problems and then do a review, answer your questions for the final exam. And hopefully I'll have an answer from Dr. Nelms about it. Matter of fact, I'll look right now because I'm a little curious. I have a feeling a little green light. And if he greens lights, I'm happy, you're happy. Hopefully. Is that your last final, by the way? On Thursday? Is that yours?
I have one on Friday.
No, yours on Friday.
You got one on Friday?
No.
Digitron.
You got Friday? You have a final on Friday? No?
Where's the
Then you're done on Thursday. So if you're done, enjoy.
Just on Friday for me.
Yeah, same time that your random is.
I had, you know, the thing about it is, it's what, when do finals start? Wednesday?
Wednesday.
Boy, I do not like finals on the last day of class in the summer because when's our first day of fall? Is it?
16th.
God, that's early.
You get a week and a half, yeah.
For me, yeah, and usually, a lot of times I have to go through graduation. This time I don't think. See, a week and a half, it's not, I like a 2-week plus break between summer and fall. I gotta go see people. And I can't Zoom my first day of class unless I'm at a conference, then I think I can get away with it. It's hard to make that work. All right, so. Here comes, ready? So take your phone out, put it on the desk next to you. Now just put it on the desk. Take your phone out of your pocket. Take your phone out of your pocket.